there's a range of masses that we believe the neutron stars can be. And the lower end of that mass range is basically what causes a star to collapse in a supernova in the first place, because a massive star, its core is almost a white dwarf, which is what our sun will end up turning into someday. It's basically a white dwarf, and when the pressure gets too high, and there's too much mass in that white dwarf, it can't hold itself up anymore, and it collapses. That mass, which is about 1.4 times the mass of our sun, is known as the Chandra-Zakhar mass. And if you put more mass onto the star than that, it will collapse and become a neutron star. So right around 1.4 solar masses is where we think the transition from a white dwarf to a neutron star exists. Now, there are other ways in which you can go through that process of collapsing from a white dwarf into a neutron star. So it might be possible to make neutron stars that are slightly less massive. And in fact, we know of neutron stars that are around 1.25 solar masses. So that lower end of the neutron star mass range, we don't know exactly what it is, but we do know that white dwarfs can't be more than 1.4, and if they are, they turn into neutron stars. The upper end of the neutron star mass range, though, where a neutron star will collapse into a black hole, because neutron stars are the closest thing that we know of in the universe to a black hole. They're the only things that have a surface, basically, but yet that surface is barely bigger than the size of a black hole, so they're very close to being black holes themselves. But how much mass a neutron star can take before it collapses into a black hole is currently an unknown. And basically this is related to nuclear physics, and it's related to Einstein's theory of general relativity. And it's thought that that number is somewhere around 3 solar masses. So we've found pulsars that are nearing 2 solar masses, and maybe, with large error bars, a couple that are slightly above 2 solar masses. Whereas just a few years ago, the largest mass neutron star was about 1.4. That we knew about. Matter of fact, neutron stars were very tightly clustered around 1.4 solar masses. And so finding this wide range of masses is giving us very large constraints on the so-called neutron star equation of state, and giving us, detailed experimental evidence, if you will, on nuclear physics.